Okay, so what were we talking about? We were talking about isometries in R3, and we were talking about the fact that if we've got a direct isometry, it would be something like this, where I've got an eigenvalue, a real eigenvalue given by 1, and unless theta is 0 or pi, I've got two complex conjugate eigenvalues, ei theta, e minus I theta. Okay, and so we said that this transformation corresponds to, there was this little drawing, to a rotation around some axis obtained by the eigenvector associated to the eigenvalue 1 of the angle theta, the theta corresponding to that part. Okay. And we said that, well, okay, that's nice, but how do I find this theta? And the first thing we said is that, well, the trace does not depend on the basis where your matrix is expressed, so that the trace of M, which I can always calculate given M, corresponds to 1 plus 2 cosine of theta, and so that you got that cosine of theta was given by the trace of M minus 1 over 2. Fine, so we need to find the theta, and so we get that theta is going to be equal to, well, arc cosine of trace of M minus 1 over 2, but the problem is that the arc cosine function gives you theta up to the sine, plus or minus. Okay, you remember your cosine is going from 1 to -1, so the arc cosine goes from 0 to pi, but you can have, for the same value of a cosine, you can have plus or minus the same angle. Okay, so using the arc cosine will give you a value, but the real value of theta, you have to determine the corresponding sine. So how are we going to do that? Well, actually, it's a long story. I'll try to make it short. It's really a calculation stuff, but we're going to find something related to the sinus of theta. Okay, and the sinus of theta, okay, maybe we don't need to do the calculations, but because it's really just a calculation trick, you can obtain it by doing the scalar product of, okay, let me use some notations, V1 cross product with V2, scalar product of that stuff with F of V2. Okay, so we should say what we have here. V1 is the same V1 as the one I used earlier. Okay, the same V1 as I used earlier. It's the eigenvector for the eigenvalue 1. Eigenvector for lambda is equal to 1. Okay, V2 is, and let's say that we have normed this one, a unit one. Okay, V2 is going to be a unit vector in E1 orthogonal. Okay, so that I would need just one more vector in V1 orthogonal to make a basis, right? And actually, if I compute the cross product V1 cross product with V2, it gives you a vector V3. And if you have normed, and if you norm this vector, you're going to get that it's V1, V2, V3 make a direct orthogonal basis of what? Of what did we say? Of R3. Okay. So if you do this computation, what's happening? So you take V3, right? Assume that you have normed V3. Right, let's write that you norm V3 here. F of V2 is actually the application M times V2. Okay, so V2 is something that lives here. V2 is a vector, a unit vector that lives here, right? You apply your transformation F. You apply your matrix M, and it makes the rotation. Okay, it makes the theta rotation. So F of V2, that's actually, you calculate that by computing the effect of matrix M on any unit vector that you have chosen V2. Okay, the thing is that this belongs to E1 orthogonal. So what's happening when you apply M, you apply the transformation to V2, actually you're getting the rotation, right? So you're going to get a vector that can be written as cosine theta times V, 2 plus sinus of theta times, well, we made our direct basis times V3. Okay, assume V2 and V3 have been normed, all right? So times V3 over V3 orthogonal. Okay, and so okay, right? So if you plug that into this scalar product, you get V3. Sorry, V3. I'll forget about the norm. We don't need actually the norm. We can make it without the norm. It doesn't matter. You get the V3 inner product with, right there, inner product with cos theta V2 plus V3 inner product with sinus of theta V3. Okay, and so as we built V3 to be the result of this calculation, V3, you know, is going to be orthogonal to V1, and V3 is also orthogonal to V2. So that part is actually equal to 0. And this part is actually equal to the sinus of theta times the norm of V3 square. Square, not cube. Okay, so what's the good point about this? If you have normed V3, then you have the sinus of theta. If you haven't normed V3, at least you have the sine S, the sine, the plus or minus of theta. Because if your angle is positive, then the sine is between 0 and pi, then the sinus is going to be positive. But if your angle is between 0 and negative pi, well, if it's your angle is negative, that sinus is going to be negative. Okay, so that's it. Let's sum that up. And we'll see about the indirect transformation after that. Okay, so this is that part, that first part here. All right, sorry about that. Okay, so given a matrix A, you first compute A times its transposed. If it's equal to the identity, then you know you have an isometry. Okay, so if the determinant is equal to 1, that's all the calculations we've just done, you know you have a rotation, but you need to find the axis and the angle. To find the axis, you find the eigenvector corresponding to eigenvalue 1. To find the angle, you first compute the trace of your matrix, and that gives you the cosine of theta, and then you compute that stuff that gives you, if you've normed everything, the sinus of theta. If you haven't normed them, it doesn't matter. You get the sine of theta. Okay, so you can identify all the characteristics of this transformation. All right, but finally, we haven't treated the case where we had an indirect isometry, the case where the determinant of A was equal to -1. And I assure you that's going to be much faster. So we need to treat the case of an indirect isometry. Indirect isometry is going to be this, this matrix here, but with a minus sign here. So what can we understand from it? So we have some matrix, indirect isometry. It's going to look like -1, 0, 0, 0, 0, and then we've got this cosine of theta, this minus sinus of theta, this sinus of theta, and this cosine of theta. Great. So, what can we do? Actually, we're going to express that as this matrix, -1, 0, 0, 0, 1, 0, 0, 1. You know what that is. Times 1, 0, 0, 0, 0, cos theta, minus sinus of theta, cos theta. Okay, to get this -1 sign, I multiply it by this here, and then the rest is the identity. Okay, good news. You know the two things we have here. We've got one part which is an orthogonal symmetry, and we've got one part which corresponds to a rotation along some axis. Okay, of some angle. Great. So what do we have here when we take the product of two matrices? It corresponds to the composition of the transformations. So we have the composition of a reflection with respect to, well, of this orthogonal symmetry, and a rotation of angle theta. So I need to indicate two more things. The characteristics of the symmetry, meaning, well, you see that this is, you've got the identity part has dimension 2, so it corresponds to a plane. So it's going to be an orthogonal symmetry with respect to a plane. So I need to find the plane, and I need to find the angle and the angle and the axis of the rotation. Good thing is that the axis of the rotation corresponds to eigenvalue 1, so that's eigenvector, sorry, for eigenvalue -1. And so that's going to be, let's call that E -1, that's going to be the span of one eigenvector. And the plane here, well, it's just what's remaining. It's going to be E -1 orthogonal. Okay? So if I'm trying to draw this, I've got that direction, E of -1, the orthogonal plane. So let's say we've got an orthogonal plane, E -1 orthogonal. And so what's happening for any point in R3? We are taking its symmetric with respect to the plane, and we're doing the rotation around this axis. Not my point should be called x, and that should be mx. All right. So again, we're doing some rotation along that plane. Well, some rotation around this axis, but of some angle theta. And but we add the rotation, the reflection with respect to the plane E1 orthogonal. And how do you find? So to find the axis, it's easy to find it corresponds to a eigenvector -1, and to find the angle, well, you've got everything expressed in that case. So in that case, the trace is -1 plus 2 cosine of theta. So you find the arc cosine, and then again you've got the same ID for the rotation part. Okay, so it's the same ID for that. Great.